A22 power series expansion of sinusoidal functions. Now we learn this equation is equivalent to harmonic oscillator. And actually, without solving harmonic oscillator mathematical solution, we experienced the oscillating behavior well before we developed the mathematical way to find out the solution. Everybody knows that pendulum oscillates. Mathematical realization shows that we cannot ignore this speed in nature unless we are living in the space with this vacuum. Anyway, the mathematical idealization is very simple to develop some idea. So why don't we scale everything, remove all of the physical scale into a simple mathematical problem? Then you will find that this is the second. I would like to talk about the basic nature of the reason why there are only two linearly independent solutions. And these linearly independent solutions spans all possible solutions of this homogeneous equation, just like the two unit Cartesian basis vector spans all of the points on the two-dimensional plane after being multiplied by real numbers and being added up together. So this dimension looks different, but in abstract mathematical sense, they are equivalent. The most important point here is that because we know the Taylor series expansion already, but we will consider in this class, we will study later. Once you know all of the derivative to any order of a function at point x0, first order, second order, and then you can make an extrapolation from a point to an arbitrary point as long as it's differentiable to all orders. So I can extend the prediction from the information at a single local structure with the derivatives. I can extend this function by integration to arbitrarily large number or arbitrarily small number. So these are key points of determining the structure of a function as a power series. However, differential equation directly tells you that there are only a few linearly independent constraints on them. What I mean is there are only a few actual independent parameters to determine the function. Why? This is why. You have a function of x. You have a second order derivative of function is just to put the negative sign on it. So if you know a function, then your second order derivative is completely determined. Aha! So when you want to expand this function as a power series of x minus x0 in powers, they are coefficients of this 2 factorial 1x minus x0 squared at double and so on. Because of this differential equation, second order differential equation tells you What about the second order derivative of x0? Because of this, second order derivative is just nothing but x0, put the negative sign on it. So it is, once you know this, and then higher order derivatives are completely determined due to the constraint of the equation. That is the powerful nature of the Newtonian mechanics. F equals ma. A is the double time derivative. And the double time derivative is completely determined by a function. Therefore, any derivatives of a third order, fourth order, I don't care. It is completely determined by the original value and first order. Then second order is determined by x, third order is determined by first order, and so on. There are only two parameters that determines this function if I have this elementary equation. You know what? They are simply sum of even function and odd function. They are cosine and sine. That's the end. Too simple. Let's see. A function, middle school students know, a function can always be decomposed into even and odd. An even function is, if I substitute minus x, I would get the same function. That's the reason why it is a symmetric, left-right symmetry. Odd function, however, their magnitude is the same, but sign is opposite. So we know there is the origin, just like sine. Magnitude is the same, this height is the same, but opposite direction, that is called odd. Any function consists of even part and odd part in general. And you know, if n is an integer, this is odd, this is even. I don't have to explain this. Okay, cosine is an even function. Let's say it's apparent. You take the double derivative of cosine, you have minus cosine. You have double derivative of sine, you have minus sine. Therefore, you find that cosine tau and sine tau, both of them are the solution of this differential equation. You know, sine is an odd function, cosine is an even function. Because sine 0 equals 0, and the limit sine x over x is 1, we find that sine can be expanded as a power series of odd powers, except that the first term, using these two facts, I can tell you the first term in this power series of sine is tau. Find the sequence ck in here. Substituting the series for y in the differential equation, let us take the derivative twice and then substitute in here and keep it as it is and substitute in there. Okay, second order differential, this derivative will give this polynomial 2k plus 1 and 2k, and power has been decreased by 2. This identity operator will leave it as it is. Now we can reorganize the sum. What I'd like to do is make these two have a single index. So I have to shift this dummy index for the first summation. This is a sum over 0 to infinity. But I know if I substitute 0, this one vanishes. So the first non-vanishing contribution comes from k is equals 1. And then why don't we shift this variable to k that runs from, if you substitute k equals 1, it is 2 times 1. This is the initial value. If I want to let it be 2 times 1, then I shift this one by 2, and then if I substitute k equals 0, still we have the same value. Aha, so this change is replacing k with k plus 1. Therefore, this is 2k plus 3, and this is 2k plus 2, and power has been shifted from 2k minus 1 to 2k plus 1. Now I can substitute this and with the same summation. As a result, what I find is a recurrence relation. This recurrence relation tells you if I know the value of a coefficient at some point, next one is completely determined by multiplying this additional factor. So recursive application of this, one by one, k to k minus 1, I have original factor, decrease them by 1. So 2k plus 2 becomes 2k, 2k plus 3 becomes 2k plus 1. I need to multiply minus 1 once again. Repeat everything until we reach C1 that we know C1 equals 1. Therefore, if I combine everything all together, it is 2k plus 3 factorial. In such a manner, I can find the kth element is, this is for the k plus 1th element. So kth element can be obtained by replacing k plus 1 with the k. So the result is this. As a result, that power series expansion is completely determined as this kind of series. Why? There was only a single parameter that is free because first order x, tau, and then cube, fifth power, anything. This one determines this, and this one determines this in series. So only two parameters survives. One parameter is for the odd function that results in sine function, and repeating the same process for the cosine case. This is, we determine the series expansion of cosine as we know in the textbook. It is developed well later, the full development of differential equation, and now we call this the Frobenius method, but the basic structure I told you is y sine and cosine. Newtonian mechanics tells you equation of motion is at most second order derivative. So once you know f of x0 and f prime of x0, simply saying initial displacement and initial velocity, two information is enough to determine everything else in the future. That's the reason why the deterministic philosophy developed due to the full establishment of Newtonian mechanics until they found the breakdown of the Newtonian mechanics due to the Einstein's relativity and quantum mechanics.